Hello, everybody, and welcome back to Physics Rich. This is your one stop channel for your preparation for IIT JEE Mains, Advanced, NEET, and AP curriculum. We are into the series of fluid mechanics, and this is the second lecture on fluid statics. So, let's begin. So, we have spoken in detail about the basics in the first lecture, and we will expand those basics and understand some new topics today, and we will also apply whatever we have learned in the previous lecture in today's class. You will learn about absolute and gauge pressure, barometer, manometer. We will learn about Pascal's laws, and we will do some practice questions which will help you get into the mood of solving good problems and help you prepare for your exams. So guys, what exactly is the absolute pressure? First of all, we need to recall about what we have learned about pressure. Pressure is normal force acting on a given surface area. It's the force which tries to pierce through a given surface area in a perpendicular direction, right? Absolute pressure means all the total force which is acting on a given surface per unit area. And of course, we're talking about the normal force. Please do not take the parallel force over here, because this parallel force is put in case of fluids by viscosity, and that we have not discussed yet. We will move to viscosity in our upcoming lectures, especially after we are done with fluid dynamics. Now, speaking of absolute pressure is the absolute amount of force, which is the total amount of force in the perpendicular direction per unit area, and it is measured relative to perfect vacuum. Now, my dear students, we have to understand that there is a huge air column right above us. Everywhere we go, there is air on the earth, and because of that air, because of the presence of so much of air, there is a pressure on the surface wherever we are. This air comprises of many molecules. These molecules, they hit whichever surface they can, and they apply a certain force, and that causes pressure. Now, if we take all the total force, divided by that area, divided by that given area on which that force is applied, we get the absolute pressure. Above all of this atmospheric layer, we have space, we have vacuum. Okay, we can approximate it to be a vacuum. Now, we calculate the absolute pressure with respect to the perfect vacuum. So that's why it's measured relative to the perfect vacuum. Now, what is the meaning of zero absolute pressure? Dear students, zero pressure means there is no force at all. Means there are no molecules hitting, and that means you are in vacuum. There is no pressure in vacuum. Why is it? Because there are no molecules that will hit. Okay, makes obvious sense. Moving on. Absolute pressure is always non-zero, and it can never be negative. Okay, it can never be negative. I should write this down. It's never negative. Okay, it's always non-zero. Why is it always non-zero? Because, well, technically there is no such thing as perfect vacuum. Okay, perfect vacuum, to establish perfect vacuum, you would require an infinite amount of force on one side to just throw all the molecules away from one given region. But then you may be asking in your head that, sir, but isn't interstellar space perfect vacuum? Well, you can approximate it to be a perfect vacuum. However, you will somehow still find one or two stray molecules here and there, right? There could be some molecule, perhaps there could be some small piece of rock floating by, and that rock, perhaps it breaks down. We don't know, and its molecules get scattered. Well, the universe is all comprised of stardust, isn't it? What is stardust? Stardust is all the things, all the matter, gases, solids, and very different kind of states of matter strewn across all the universe. So there is no such thing as perfect vacuum. So there is always some amount of pressure. Wherever you go, there is some amount of pressure. Okay? So there's no such thing as absolute vacuum. It's always non-zero and it can possibly never be negative. Okay? Now, if we have a container and this container has a certain amount of fluid filled up to height h, then the absolute pressure at this point, will be given as P naught plus rho gh. And I have already explained to you what P naught is. P naught is the pressure due to the atmosphere. And rho gh is the pressure due to the liquid above this point. So this absolute pressure becomes pressure due to the air column and pressure due to the water column. All right. So that's the absolute pressure. I hope you understood. Now we speak of gauge pressure. And gauge pressure is measured relative to the atmospheric pressure. It can be positive, it can be zero, or it can be negative. Gauge pressure is absolute pressure minus the PATM. So you see, guys, that if there is a place on the earth where the pressure is lesser than the atmospheric pressure, first of all, is that even possible? Yes, of course, it is possible. You can take a container, you can take a can, and then you can take a pump and suck air out of it. Inside of the container, inside of the can, you will have some pressure which will be lesser than the atmospheric pressure. So what's the gauge pressure in there? The gauge pressure is negative. So whenever you find out that the gauge pressure of a given place is negative, it means that it is lesser than the atmospheric pressure. Usually the gauge pressure is positive, especially if you go inside perhaps some water body. Let's say you have a lake or you have a pond or you want to dive into the sea and you jump in there and you go to some depth and you try to measure the pressure over there. You will measure the gauge pressure. You will be measuring the gauge pressure with whatever device you will be taking. And that will come out to be positive. So if atmospheric pressure is, well, 10 raised to power 5 Pascal, we have approximated it to 10 raised to power 5 Pascal. Absolute pressure, let's say we are at some place where there is a very high amount of absolute pressure, then what would be our gauge pressure? The gauge pressure that we would find in our calculations would be the subtraction of these two terms, which I will get simply as 2 into 10 to the power 5 Pascal, which is the subtraction of these two. Now, if ever I assume that this is due to a water column, then how deep would this water column have to be? I would just do rho gh equals to the gauge pressure and I would calculate the height, which will come out from this formula. All right. Now, what is rho? Rho is the density of water. G I have approximated. It's the acceleration due to gravity, which I have approximated to be equal to 10. And if I take the ratio, it comes out to be 20 meters. So at 20 meters depth, I will not have a pressure of 2 into 10 to the power 5 Pascal. It's a very common mistake that students do. If I ask them, what is the pressure at 20 meters depth in some water body? More often than not, students report this value. They find out rho gh and they find out that this is equals to 2 into 10 to the power 5 Pascal. But it's wrong because the pressure at a 20-meter depth is going to be the absolute value. It's not going to be the gauge value. So please be sure and do not make mistake between gauge pressure and absolute pressure. More often than not, you will have to add the atmospheric pressure in your calculations. Whenever you find a free surface of the liquid, always make sure that you're adding atmospheric pressure and you're taking atmospheric pressure into your calculations. Let's move on to barometer. So you guys can see that there is this medieval looking gentleman who is perhaps doing some experiment. And here this gentleman seems to be showing the experiment to his mates. And here, well, the experiment is actually shown to you what it is. Well, this man is called Evangelista Torricelli. Because the pronunciation is Italian, I may not be pronouncing it wrong. I mean, I could be pronouncing it wrong. I'm not Italian, I don't know how to pronounce that. But this person, Torricelli, okay? Now, this person figured out that if I take a very long glass tube, if I take a very long glass tube, sufficient length, let's say perhaps 1 meter long, if I start filling mercury in it. Now, what he did was, he took the tube, filled mercury in it, and then closed it from one end. You can see that? You can see this way? He closed it from one end, and then he took his hand inside of this liquid and then removed his hand from underneath. Now, what does he see? He sees that the liquid doesn't flow out, which was actually quite surprising. This is what you would expect, that the liquid just simply flow out from here. But it doesn't. Because what we are doing, we are actually seeing the barometer in action. So barometer measures the pressure of the atmosphere. And how does it do that? That is what we will try to understand. So my dear students, take note of this word called baros. You will also hear about something called baryons when you will learn about atomic physics. Baryons are subatomic particles that provide weight or mass to anything. Baros means weight, and a barometer is hence a weight measurer. Atmospheric pressure is due to the weight of the column of air above a given point on the earth. Okay? Atmospheric pressure, all the pressure that we notice, is because there is a huge column of air sitting on top of our head. Okay, kind of feels unbelievable, but that's the truth. There is a huge amount of air sitting on our head. And you may be wondering, if there is so much of air sitting on our head, why are we not getting crushed? Guys, we're not getting crushed because our bodies also have our blood pressure, right? And our bodies have evolved over billions of years to withstand this kind of atmospheric pressure. Which means that if you were to go deep into the sea, very, very deep into the sea, perhaps to the depth of maybe a few kilometers, you will find that the pressure over there would be so high that the animals that live over there, they would have evolved to be in that sort of pressure, which is why those animals, they would never, never, never come to the surface. Exactly like how you would never want to go into the space without a space suit. Because if you do so, your blood pressure would rip your body apart. Exactly like that. If those specific marine animals who have evolved to live in such high pressures underneath the water, if they would ever to come up to the surface, they would die, which is why they don't. Okay. Now, what do we have here? We have the understanding of barometer. Barometer is the weight measurer. Atmospheric pressure is essentially due to the weight of the air column above us. Now you see, guys, this is exactly what barometer is. And yeah, this is the name of the person. I still cannot pronounce it. Please, my bad. But this is the device, and that's the barometer. So what do we have here? We have the atmospheric pressure pushing over here, and that atmospheric pressure which pushes, like you can imagine a lot of molecules, they're just coming and hitting onto this surface. The liquid actually does want to flow out. The liquid wants to flow out of here, but it can't. It can't because these molecules, the molecules of air, they won't let it. Okay, they won't let it. Here we have vacuum. Okay, here we have vacuum. The mercury wants to flow out, but it can't because it is being stopped by the molecules that are present over here. Interesting, right? So, if at all you were to go to a place where the pressure is actually low, let's say you go to, perhaps you visit a very nice place in Himachal or Kashmir, which is on a very high altitude. If you go there, you find that the atmospheric pressure is actually less. There's low pressure, and this column would actually not rise enough. The understanding that we get from here is that barometer measures weight of the air column above us. As you go higher and higher and higher, the weight above you would reduce, and that's why the height in the barometer would also reduce. Okay, so the height of the mercury directly represents the pressure due to air or the weight of air column. Okay, I hope that clarifies things. Now you see that barometer reading will change whenever this weight changes. And when will this weight change? Whenever you will be in a place which will have less air above you compared to the sea level. I hope you understand. All right. And that will obviously happen if you go to higher altitudes. All right. So the understanding is that this liquid doesn't pour out, and the reason is atmospheric pressure. Atmospheric pressure tries to push it down so that it can keep up. Now, I can give you a lot of examples like this. Like, for example, let's say I have a, a table. Okay, let's say I have a table. Now, this table is made of a top which is perfectly smooth. Let's just assume that it's perfectly smooth. Now, if I take a rubber pad, okay, a perfectly nice round circular rubber pad, and I put it on the table, what's going to happen? You will see that if I put it on the table and I remove all the air from underneath it, the rubber and the table will be stuck. They will be stuck so much that if I try to lift that rubber pad with the help of a hook, I will be lifting the entire table with it. This is the rubber pad, and you will find that the entire table will be just simply hanging. Why would that be? It would be so because the air from underneath would be pushing the table onto the rubber. All right, onto the rubber pad. That is how great the atmospheric pressure is. What do you see over here? You see that the molecules of the air, they hit the surface, and the mercury doesn't flow out because the force that this part of the mercury is applying over here, these molecules are applying the same kind of force, and this is sort of like they're canceling out. And at the same level of the liquid, you have the same pressure. Okay, and we find out that 76 centimeter of mercury is the height. Well, you remember we discussed that 76 centimeter is the unit of pressure of mercury. But of course, pressure cannot be measured in the units of length, right? But what it means is that if there is a column of 76 centimeters of mercury, it will apply the same amount of pressure as the entire air column above us. That's what it means. Okay. Obviously, it doesn't mean that 76 centimeters is the same thing as 1 atmospheric pressure. No, it doesn't mean that way. You don't mean to put it that way. It means that a column of 76 centimeters of mercury would apply the same pressure as the entire atmosphere does. Okay, and you can calculate it from here. We take mercury over here. Because it's a very dense liquid, it's shiny, it doesn't evaporate, it doesn't boil so easily. There are so many reasons as to why you can choose mercury over here in the barometer. It's like the densest possible liquid. It's got a relative density with respect to water, a specific gravity of 13.6, which means that its density is 13600, 13,600 kg per meter cube. That's like very dense. And if I apply the concept of pressure over here, okay, there is P naught, which is acting over here. Here we have vacuum. Okay, here we have vacuum, and vacuum has a pressure of 0. Again, like I said, it's not perfect vacuum, but you can approximate it. So 0 plus rho hg gh. What is rho hg? Rho hg is, well, this. G is the acceleration due to gravity. We put that equal to 9.8. And if you calculate the h from here, comes out as 76 centimeters. And of course, we do this at the sea level. We do not do this on the mountains, all right? Because at the mountains, this would be lesser than 76. This value would be lesser than 76, okay? Now, you see, if I try to do this exact same thing with water, I get a height of 10.3 meters. Now that's a very, very large amount of height. It's kind of like 33, 34 feet, 3-story tall building, and it's practically impossible to build a barometer that is of that kind of height. Okay. So you see that um, water can rise up to a height of 10.3 meters. If at all we assume that there is vacuum at top and atmospheric pressure pushes it to 10.3 meters. Now, I want to clear some confusions that some students may have at this point. You guys use a straw to drink perhaps soft drinks. Soft drink like any soft drink, you can use a straw and you can drink through it, right? Now try to do one thing. Well, take a straw, put that in your mouth. Take another straw, put that in your mouth too. But take the first straw, put it in your drink, and the other straw, don't put it in your drink. And now try to drink your soft drink. And you'll realize you'll not be able to. Do you know why? Because you see the other soft drink, the other straw is not letting you drink the soft drink because it's not creating any pressure difference. You think that we can just scoop something in like with our mouth. It depends upon our ability to suck it, but it doesn't work that way. Because the lowest pressure that you can create has a limit, and that limit is vacuum. Okay, that limit is vacuum. You cannot go lesser than zero pressure. And that is why there is a limit to how much pressure difference you can create. It's actually the difference of the pressure that you create that causes the liquid to flow. But you cannot create a difference more than the atmospheric pressure itself because the lowest pressure that you can generate is zero. All right. So, if at all we have a faulty barometer, this is not exact vacuum. There is some pressure over here. In that case, the pressure of this air plus the rho GH will give us the PATM, and obviously this height would be less compared to 76 centimeters. Okay. And we are obviously applying the concept that at the same pressure exists at the same horizontal level. All right. So yeah, why mercury? Mercury because it is dense, does not evaporate, it's shiny, it's opaque. And of course, why not water? Because firstly, 10.3 meters is a lot. Okay. Secondly, as it goes up, in fact, you know what? It can barely even reach 10.3 because before it reaches 10.3, it begins to boil. It begins to boil and starts to evaporate. Okay. It's very easy to evaporate. And if you want to see that water is rising, you're going to have to probably put some color in it. It doesn't, it's transparent and it's not opaque and doesn't shine. So handling water in such a barometric situation is not a wise thing. But remember guys, all pressure is due to the height. It's not due to the length. In which case, if I take a barometric tube and I tilt it at this angle, tilt it at 37 degrees, what do I get? I get that the L length of this barometer will be filled, but the height will still be 76 centimeter. Now you see that this L length corresponds to L sine 37 of the height. So I'll just try to show you with the help of a small triangle over here. You can see this triangle. All right. This length is, well, L. Okay. This length is L. All right. And this length is L sine 37. And we are interested in this length. So L sine 37 becomes equals to 76 centimeter. And you get 127 centimeter as your answer because sine 37 is simply 0.6. Now, like I was telling you, that there is a minimum value of pressure that you can have, which is 0. So, if you take a pump which is above, all right, this is the water level, and you are trying to pull the water from this reservoir, then please mind that you can only pull up to 10.3 meters. You cannot pull water more than 10.3 meters because the lowest pressure that you can create is 0 and the atmospheric pressure will push it down, but it will not be able to pull it up more than 10.3 meters. And that's the reason why we use submersible pumps. This is a submersible pump. And this kind of a pump is put inside the reservoir. Okay, it's better you put a pump over here, all right, because the maximum pressure that you can create has no limit. You can create as much pressure as you want. You can create even 70, 100, 200 atmospheric pressure, and it can just throw the water out. Submersible pumps are used to move liquids by being fully submerged. Okay, these pumps are fully submerged, and that's why they are ideal for drawing water from deep wells. Okay, very deep wells. If you want to pull water out of very deep wells, you must use a submersible pump because you cannot use an overhead pump for more than 10.3 meters of height. Okay. Next, we have a situation. Hulk is very thirsty and he wants to drink the entire pond. Can he drink the entire pond even if he is very, very thirsty? So, my dear students, the answer is, well, it depends. It depends upon what is the difference between this point and this point. Okay. Now, he wants to drink the entire pond. Okay, let's say this itself is 10.3. But will Hulk be able to drink more water if this height is more than 10.3 meters? And the answer is, well, even if it is Hulk, it doesn't matter. Because what he's doing is that he's creating vacuum in his mouth and atmospheric pressure is pushing down the water and then the water is flowing into his mouth. But once it goes down in such a way that this becomes 10.3 meters, that's it. Hulk is not going to be able to drink more than that. Okay, then he's going to have to jump inside the liquid and he's going to perhaps have to move from here to here. Okay, then Hulk is going to have to jump over here and then he's going to have to drink more. Okay, he's going to have to keep going downwards in order to drink the water. Okay, let's put Hulk back into his place. Oh, we're sorry, Mr. Hulk. We don't want to bother you anymore. Okay, let's move on to Pascal's law. Let's talk about Pascal's law. Pascal's law, well, it's the principle, it's actually a very fundamental, most important principle. It just says that whatever pressure you apply in one point gets transmitted equally. Now you see that if I apply a P amount of pressure over here, okay, if I apply P amount of pressure over here, a P amount of pressure over here, then at every point I will see that P amount of pressure gets increased. Let's say this height is H1, okay. If this height is H1, then the pressure over here must be P naught plus rho g H1. But because I have put a P extra pressure, that's why this point will also have an extra P pressure. This point will also have an extra P pressure, especially because I am pushing it down, because I'm pushing this piston downwards, all right. So this pressure is P naught plus rho gh. This is P naught plus rho gh plus an extra pressure P is added over here. And this extra pressure P is going to be put on each and every point inside of this fluid, okay. So whatever pressure you apply from one side can apply the same amount of pressure onto the other side. And here you can see that a man can simply move his hand and can lift an entire vehicle. How is that possible? That is possible because if he applies a force on a very small area, then the pressure that gets generated is F1 upon A1. All right. The pressure is his force, the force that he's applying, divided by his area. And this pressure gets transmitted perfectly. And if this area is very big, then the force that gets generated over here is actually quite large. All right. Now, this force becomes equals to F2 equals to F1 times A2 upon A1. And as you see over here that this is A2, this is the area of the other side of this device where the car is resting. Okay, this area is like quite large. Large area upon small area gives me a very large number, and that gives me a very big multiple to F1, and F1 was the force applied by the man. So it sort of works like a force multiplier. All right, it sort of works like if you push with some force on the other side, it's going to give you a large amount of force. Okay, so this is the concept which is even used in braking, in brakes of very large vehicles. If we have like a very large vehicle, you want to apply a very high amount of force, you can apply a simple small amount of force on one side on the brake, and then it gets transmitted to a very large amount of force. So you can see that this is a hydraulic lift. The input area, oh, by the way, this is a JEE 25 question, guys. A very simple, very good question. So it says that the area on one side is 6 centimeters square, and on the output side it is 1,500 centimeters square. And we see that there's a 100 Newton force applied onto the input. Okay. And what it means is that if we apply F1 upon A1 equals to F2 upon A2, we simply get 100 upon 6. 100 because this is 100 Newton force applied over the 6 centimeter square area. This is the 6 centimeter square area, and this is a 100 Newton force onto the left side. We get a 25,000 Newton force onto the other side because this area is 1500. Okay, so this force is coming out to be 25,000 Newton. It also says that the piston is raised by the height of 20 centimeters, which means this side is raised up by a height of how much? 20 centimeter. And because it is raised by a height of 20 centimeters, we can say that the work done will be the force which we just found out times 20 centimeters. So this comes out to be 5,000 joules. If we just multiply 25,000 with 20 upon 100, because it's in centimeters, comes out to be 5,000 joules. And you were supposed to put your answer in kilojoules, so your answer would simply be 5. Okay. Moving on to the next part. Let's now talk about something called a manometer. Now, a manometer is a device which is used to measure the pressure of gas in a container. So it kind of works very similarly to a barometer, except that it is not connected to the atmosphere on either side. It's connected to a gas on one side. So this gas molecules, they come over here and they push the liquid down here, and the liquid tries to rise up. Okay, and if it rises by a height h, we can simply say that the pressure at this point for this liquid would be P atm plus rho gh. P naught plus rho gh. You see, this rho gh is the gauge pressure which we were discussing earlier. P at the point 2 is the absolute pressure, and the pressure at point 2 and pressure at point 1 will become equal. What is P1? P1 is the pressure of the gas, and if you use this fundamental, you can find what is the pressure in the gas depending upon the height of the liquid column. Now check this out. What's happening here? We have a gas, we have a certain height of the liquid over here, 1 meter height of the liquid over here. Okay, and we are supposed to find out what's the pressure of the gas. So how do we do? How do we do it? Well, pressure at this point should be equal to pressure at this point. Okay, I hope that is clear. Pressure at this point should be the same as pressure at this point. What is the pressure at this point? It is the pressure due to the atmosphere, due to air over here, plus the pressure because of this liquid column. So I have added the pressure of the atmosphere, which is 10 raised to power 5. And then I've taken rho GH. Now this is H2O. H2 is just the water. Water has a density of 10 raised to power 3. I have taken G to be equal to 10 and H to be equal to 1 because this is given to be 1 meter. If I add all of this, what do I get? I get 100,000 and a 10,000. Okay, so I get a total of, well, I should just write it over here, 100,000. 1 second. Uh-oh. Yeah. So this is 100,000 and a 10,000. So it's 110,000 Pascal. All right. So that's the pressure of the gas. All right. Let's now talk about something called a U-tube. Well, not this U-tube. This is a U-shaped tube, which is why we call it a U-tube. Okay. Now, this is filled with water and that's in equilibrium. Okay. So if you fill it with water, you will realize that it will be in such a way that on both sides you will have the same height. Okay. Now what happens? You take some oil. Okay, there is some oil. Now what oil are we talking about? We're talking about some oil that has a specific gravity of 0.8. Sg stands for specific gravity. And now you fill it onto one side. Okay, this is oil. And this oil does not mix with this water. Now he's asking us, by what height will H2O rise? Will water rise on the other side? Okay, and you have filled it by 10 centimeters. Okay, so you can pause the video and you can think about it and then you can listen to the explanation. So here's the explanation. So you see guys that this was the original situation. Now you poured oil from one side and this is how much oil you have poured. This thing moves down by x, by a length of x. You can see that this thing has moved down by a length of x. But don't you think that if this moves down by a length of x, this will also rise by a length of x? So it's kind of like this is how the water was filled. This went down, this went up. The amount with which it will go down, same amount will be rising onto this side because this is a U-tube which has both these two sides be identical. This goes down, this goes up. That's why we have a length of 2x over here. If it goes down by x, we have a length of 2x over here. And we will report our answer as x because he's asking that by how much does water rise from one side. So original length was this, but it rises by x. But what is this height? This is going to be 2x. So the difference between this and this is going to be 2x. So we'll just calculate from here. What is the pressure at this point? It is P naught plus rho naught G H naught. And that should be equal to P naught plus rho W G 2x. What is rho naught? Actually, this is rho O. We can call it rho oil. G H H O. O stands for oil. So this P naught is going to get cancelled. Okay, let's just cancel this P naught. Cancel, cancel. Okay. So G will also cancel. All right. Rho O is, well, the density of the oil which was given to you. And HO is the height of 10 centimeters. And we are supposed to find out X. All right. So we can put the values. We can see that what does this come out as? Rho O HO upon rho W equals 2x. Rho O upon rho W is the SG, of the oil. Because the density of the oil divided by the density of water is the specific gravity. And in the question, we have been given the specific gravity. Specific gravity is, well, 0.8. So we'll just put 0.8 over here. Height of the oil is given to you as 10 centimeters. So I'll just put 10 over here. That should be equal to twice of x. X From here, it will come out to be 8 upon 2, which is equal to 4 centimeter. And that's my answer. So the water will rise by a height of 4 centimeters. Okay. People would make a mistake over here. They would just put X over here. I've seen students making this kind of a mistake, but try to not make this mistake, guys. Okay. Now, what is happening over here? What will be the ratio of the heights of Hg and H2O if their interface is in the middle of YouTube? Very interesting. So you see, guys, that let's say if I take this to be the height H1 and this to be the height H2, then what's happening at the interface? Of course, you know that mercury and water, they will not mix with each other. However, we will understand that at this point, water will be trying to push into mercury and mercury will be trying to push into water. So the pressure due to both these should be equal. So we'll just write P naught. P naught is the pressure over here plus density of water times G times H1. H1 is the height of the water column. Should be equal to P naught. You can see P naught will be also acting on the mercury. Okay, air will also be acting on the mercury. PATM, atmospheric pressure, doesn't spare anybody. Okay, plus density of Hg times G times height of Hg. Again, we will cancel P naught with P naught, we will cancel G with G, and we will get, what is he asking? He's asking heights of Hg and H2O. So height of Hg upon height of H2O. Okay, we have put this as H1. That's our answer basically. Should be density of Hg upon density of water. All right. No, I think this will be the opposite. It will be the opposite. So we'll take the H1 over here and Hg will go over there. So it will become rho W upon rho He. Yeah. It will be the opposite. It will not be rho Hg upon rho W. Just do a simple cross multiplication. So you see, guys, that the density of Hg is 13.6 times the density of water. So this will be rho W and this is 13.6 times rho W. So my answer is actually 1 upon 13.6. Okay. So whatever this height is going to be 13.6 times lesser than this. Okay. In fact, guys, you know what? 76 centimeter, if you remember, was the height of mercury. Multiply that with 13.6, you get 10.3 meters. Okay. Let's take a look at this problem from JEE 2014. See what's happening over here. There is an open glass tube. There's the open glass tube. Okay. And we have immersed it. We have immersed it in mercury. We have immersed it inside mercury. Okay. And this is 8 centimeter. This length is 8 centimeter. It's a very beautiful question, guys. Please pay attention. There is 8 centimeter of mercury over here, of air over here. And underneath there's mercury. Okay. Now what do? You close it. Then you close it. Okay. And you close it. And then you stretch it until you reach 54 centimeters. So first you have 8 centimeters and then you keep stretching it until you reach 54 centimeters. All right. So 54 minus 8 is 46. So basically you have stretched it further by 46 centimeters. Okay. So that's what he's saying. So the open end of the tube is then closed and sealed, and then the tube is raised vertically by an additional 46 centimeters. So you reach 54. What will be the length of the air column above mercury now? So we will have some, like there is, of course, this PATM over here. We close it and then we pull it. You will realize that the air pressure from the outside will push some mercury in this tube and it will reach certain height. He's asking, what will be the length of the air column above mercury? So either you find the length of the mercury column or you find the length of the air column. Either which way you can find the answer. Okay. So how do you do this? So my dear students, how exactly do we do this? See, try to understand. What is the pressure in the initial situation in this open tube? This little air column that you see. It's PATM, right? And PATM can be taken to be 76 centimeters of mercury. Okay, fine. Now, why am I doing that? I'm doing that because they are pulling it in centimeters. Fair enough. Let's pull it up. Let's assume that this is X. What is X now? X is the length of this air column now. This is not going to be 8 centimeters. Otherwise, it would not even be a question, right? This is X. X is not 8 centimeters. It's going to change. It's going to be different. Okay. In fact, when we find X later on, you realize that it comes out to be 16 centimeters actually. Okay. You can see it comes out to be 16 centimeters. It's not showing over here, but yeah, if I raise the slide slightly above, you can realize this is actually 16 centimeters. This is my answer, but I'll tell you how I got to the answer. So assume that this is X. This is going to be 54 minus X, because the total is 54. But you see, guys, that the number of air molecules inside and the number of molecules air molecules inside are going to be same. Okay, they are going to be same. Do you think they will lose energy? They will not lose energy, right? Do you think they will lose temperature? No, they will not lose temperature. Temperature is the indication of their energy, right? They will not lose any energy. They will not lose any temperature. And because they will not lose any temperature, the product of their pressure and volume has to remain the same. Because for gases, we can write a PV equals to nRT sort of a situation, where if T is the same, then the product of PV remains the same. So pressure over here is 76. The volume over here is 8. Later on, the volume over here is proportional to X, but now what is the pressure? So guys, the pressure over here is gonna be 76 minus 54 minus X. Now, how did I find that out? I found that out because at this level, what is the atmospheric pressure? 76. And what is this 54 minus X? This is due to mercury. All right. So at this level, the pressure should be same. So whatever this pressure is, P plus 54 minus X, I mean pressure in centimeters, plus 54 minus X should be equal to 76. And that's what I've used over here. That pressure becomes 76 minus 54 minus X. And then I multiply it with the height. And this height represents the volume. Because, well, volume is equals to area times height. Okay, you can actually you can say that this is area over here and area over here, but doesn't really matter. These area terms will get cancelled. And then we solve a little bit, we do a little bit of quadratic, and we come to a conclusion that X is coming out to be equal to minus 38 or 16. Of course, you reject the minus 38 and you accept the 16. I would like you guys to pause the video at this point and solve this for yourself. Let's now move on to another beautiful problem from JEE 14. And this is going to be the last problem for today. Okay. And I'm going to tell you how most people approach this problem. And I'm also going to tell you one of my very amazing students, Mr. Arish, he gave me a beautiful solution to this problem. And I was amazed by it. And I would like to thank him for giving this solution. So let me explain to you how this works. So we have a circular tube. Okay, we have a circular tube. And in this circular tube, there is a fluid filled such that this fluid has a D1 density and this other fluid has a D2 density. Okay. And clearly you can see that the density of D1 will be more than the density of D2. And that's the reason why D2 is slightly higher up, is pushed slightly higher up, and D1 is pushed down. And it says that they both make the same 90 degrees angle at the center. Okay. Which means that this arc length and this arc length must definitely be the same because the angle that they're subtending are the same. And they have given you this angle alpha is present, and then he's asking you to find the ratio of D1 and D2. So how do we do this problem? So I want to tell you the conventional method, and then I will tell you Arish's method to do this. So let's go. So what do we see over here? We see that there is certain height of this part. That height will be r sine alpha. Okay. And then there will be certain height because of this part also. which will be r sine 90 minus alpha, okay, which is r cos alpha. So I have taken r cos alpha and r sine alpha is the total height, vertical height for this part. And then I multiply it with d2g. d2 because this is density and g will because rho gh. And what about this part? For this part, I will find that there is a certain height due to this and there is a certain height due to this. Okay. This height will be, this height you can see it's r minus r cos 90 minus alpha, and this height will be r minus r cos alpha. Okay. If I subtract these two, this is what it comes out to be. And then when I equate it, you see the r terms will get cancelled. All the r terms will get cancelled. And then simply you'll get the ratio of d1 and d2 as cos alpha plus sin alpha upon cos alpha minus sin alpha. You divide the both numerator and denominator by cos alpha, you get this answer. All this is nice and dandy until you realize the brilliance of my dear Arish. What happens here? Arish says, sir, we have d1 upon d2, right? What if d1 was 0 and d2 was very large? What would happen? Then in that case, this alpha should be 45 degrees because this liquid will sit exactly in the center. All right. I should get this ratio to be 0. Which of the options do you think do that? Which of the options do you think becomes 0 if you put alpha equal to 45? Well, d2 is 0, right? No. So we are not looking for 0. We're looking for infinity. I'm sorry. d2 is 0, guys. d2 is 0. d1 is finite. Okay. So we are looking for infinity because d2 is in the denominator. So which of the options they become infinite? So tan 45 is 1, right? Tan 45 is 1. Sin 45 is 1 by root 2. Cos 45, 1 by root 2. This clearly does not become infinite. Does not become infinite. Also does not become